The material that we learned yesterday, it was about the attention. So we know how to calculate the attention, and at the end, we got the attention output, or we got the attention value. Now, uh, we can try to look at more details, especially when we are doing the attention. There might be some other issue. So, for example, the attention can be more than one. The attention that we looked at yesterday, it was only one, which is the word kind. But there might be a lot of attention in your sentence. For example, this one. Park is very cute and he is a dog. Okay. If you look at this word, somehow it's kind of confusing. Park, okay, is very cute. So we thought that Park might be a person, but actually he is a dog. So we can know that Park is a dog, and the Park is a male dog. Okay. Then it means based on this sentence, we can pay more attention to some of the words. For example, we can understand that Park is a male because we know the word he. And we know that Park is a dog because there is an explanation about the word dog. Then you can see from this figure, this word he is more relevant to this word. And he is also more relevant to this word. However, he and n, I think this is not that relevant, or we call it less relevant. He and is, we know that after he, it will be followed by a kind of verb. This is. He and cute, so maybe this is not that relevant. Yeah. He and so it is not that relevant too. You can understand from the materials. Last time we learned about the skip gram. So in the skip gram, we try to look at the neighborhood of the word. What is the neighborhood of he? So we can see and, cute, is, and a. But actually, it is not relevant. The relevant words are very far from he, and is also very far from he on the left and on the right. And we can try something with the attention. So we can put a kind of index. So for every word, this one, we can create token. So this is token 1, token 2, token 3, and so on. And after we have the token, we can create the word embedding. The word embedding, you can do any kind of encoding, or you can use any methods before the methods that we learned, like TF, IDF, or using the pack of words, using one-hot encoding, and etc. And then we can calculate the weight based on this encoding. And at the end, we can have the word embedding with context. So the context means we know the word he, and it will be more relevant to this word, and this will be more relevant to the word dog. So the attention, as we already learned yesterday, we have the embedding, And after we have the embedding, we will multiply with the key and the value. And also we need to have the query. So if you look at the example yesterday, the query equals to 2. Okay. So for simplicity, we have only a single number. But actually, when you are doing with this kind of attention block, you need to have a matrix, or yeah, this kind of layer, it requires a factor. We have a factor here. We have another factor. We have another factor. After we know those factors, then we can do the mathmul. So mathmul means matrix multiplication. After we do the matrix multiplication, we will normalize. So we can get a kind of weight. And after we got the weight, again, we will do the matrix multiplication with the value. Okay. We will do the matrix multiplication with the value, and at the end, we will get the attention values. So this is what we already learned yesterday. We have a simple Q, we have K, and then we multiply Q with K, and then we normalize with softmax. And then after we got the value, after the softmax, we multiply with the values, and at the end, we got the attention score. If we are doing with the feed forward network, so if we do with the feed forward neural network, then it will be only one time from the embedding until we got the attention value. If we need to do the optimized weight, if we want to find the optimized weight, then we can do the back propagation. So the back propagation, it will be back to the keys and the values. We will update those values, and also we can update the queries. And again, we do the same matrix multiplication for some iteration. So this is the explanation. Park is very cute and he is a dog. Park, cute, and he. So you can see Park, cute, and he should have some significance or relevance with the word dog. So it is relevant with dog. This word say that the dog's name is Park. It is a male dog, and that he is a cute dog. When you learn about the attention mechanism, we have only one attention. So one attention, like what we looked at before, we have only Q. Q, which is about the word kind. So if we have only the word, one word, this one attention mechanism works. But if there are many words, like this one, Park, cute, and he, so those words, we need to pay more attention for this sentence. Then just one attention mechanism may not be able to correctly identify these three words as relevant to dog. If you just look at Park and dog, so it is only one meaning. But if we look at he and dog, okay, we know that the dog is a male. Cute, okay, this is more, we have more confidence that this dog is cute and this dog is male, and we are still discussing about a dog. So we can say that 3 attentions are better to signify the 3 words with the word dog. Then we will focus on those 3 words. That's why we will need 3 attention. So how we can do this 3 attention? We can apply the multi-head attention. So the multi-head attention means for the queries, we can have some factors. For the keys, we also have some factors. For the values, we can have some factors. And after we do the multiplication for the key and query, we will normalize and we will get weight. So there will be 3 kind of weights because we have 3 kind of attention. We have the attention for bug, we have attention for a kid, and we have the attention for a key. So after we have this 3 attention, then we can do the multiplication with the value, and we will get 3 kind of attention. Attention 1, which is about the word bug, the attention 2, which is about the word cute, and the attention 3, which is about the word he, to represent about dog. And after we got these 3 attention, we can concatenate. We call it concatenate, or we call it, this is combine. After we combine, and sometimes we need to have a dense network in the neural network. At the end, we will get the value for the final attention. In some cases, if you need to do the back propagation, then after you got the attention, you will go back to update the key, the queries, and the values. So this is the multi-head attention. It means we are looking at the words which are relevant to another word. In the literature, so if you look at the research paper, there are many kind of attention scores. The one that I explained to you is the initial attention mechanism, but there are other works that propose the attention scores. So there are several ways to obtain the attention scores and various types of attention score functions. For example, you can use the dot. Dot means just multiplication. What we did before, it is a multiplication. So that's the very basic one. The other kind of score is using the scale dot. So they apply the same mechanism, the multiplication, but at the end they will divide with the number of data. Okay, how many words do you have? And they will do the square root. The other kind of works, you can see if it is a general. So this is just a matrix multiplication. A multiplication of S, W, and X. So S is the score that we got. W is the weight, and X is the hidden state. We can do with the concatenation. It means somehow we can apply the tangent function. And yeah, the other kind of scoring is using the softmax. So we try to look the location, where is the word, and whether the word will be important if it is in the first or in the second or in any position, and so on. So there are many kind of attention score. If you need this one, you can refer to this one for your future works. Now let's discuss about the transformer. Obviously, we focus on the attention. After we learn about the attention, yeah, we can look into the details about transformer. So what is transformer? The transformer, it a very relevant works for the NLP, especially for the generative AI, such as the ChatGPT and other things. Because when we are doing with the deep learning model, so uh, it still have some issues, especially when we are doing with the big data, with the large data. So we need to handle a lot of things such as the computational. But the transformer model, it works better than the deep learning models, and many people try to apply the transformer model in recent days. Instead of the deep learning model, this is the basic, so they now go to the transformer models. Of course, when you do with the transformer model, you need the high computational hardware such as the GPU. The transformer architecture, if you look at this one, maybe it is good to see the right section, this one. If you still remember the attention mechanism, what is the attention mechanism? We want to put some attention based on the key, on the value, when we have the Q, okay. And then we will do the multiplication between the Q and K. After we do the softmax, we will get the weight, and we will do the multiplication with the value. So we do this attention, and this attention happens after we do the encoding. After we do the encoding, we will do this attention, and after we do this attention, we will do the decoding. Okay. So we call this is the sequence to sequence. So the attention mechanism happens in the middle, okay. And for all the architecture, they will perform this one, encoder and decoder. And now for the decoder and encoder, we know that there is also a kind of semantic or context before we do the decoder. You can see from this figure, if we have the input, we will fit into the encoder. And after we do the encoder, we will fit it into the decoder. Sometimes the output from this one, it will be used for the input of this decoder, and then we will do another output. So we learn about this one in the sequence to sequence. And the transformer architecture, we can look into the detail something like this one. So this is the encoder part. This is the decoder part. And for every of this, we will do some more processing. For example, in the input section. So there will be an input embedding. And then we also do the positional embedding. For the encoder, we will do the multi-head attention. and then we will do the add and normalization. We will do the feed forward, and we will do the add and normalization. So this is the encoding. This is only for the encoding. You know the multi-head attention. So in the previous section, I mentioned to you the multi-head attention. If we have three words, that we need to pay attention, then there will be several head attention. So after we do the encoder, we will go to the decoder, and this decoder, again, there are some components inside the decoder. So we will do the mask multi-head attention, and then we go forward into the multi-head attention. So this mask multi-head attention, it is from the output, okay, the output given by this network, and this will be again embedded, and we have another positional embedding for this mask multi-head attention. So we will learn more about the mask. What is mask? We will learn more about this mask maybe next week. But let's say this is based on the multi-head attention. And we have another multi-head attention, and we go to the feed forward, and at the end, we will perform the linear transformation and softmax to get the output probabilities. So if you look at the architecture, the architecture of transformer, they apply the attention. They apply the attention, and they apply the neural network. They apply the attention. So attention mechanism is the basis for the transformer. Yeah, in the detail, yeah, we can look the transformer something like this one. If you know the word, okay, let's say I have an input, this one. So you can do the tokenization. I think you already know what is tokenization. In the tokenization, we will split the word into one, the sentence into one word, and one word, and one word. So we can get the token. In this case, we can get 4 tokens. After that, we will do the embedding. So the embedding means you can transform the text into a value, like maybe using the TF-IDF or using the back of words. And then we will do the positional embedding. So we will take a look about this positional embedding or the positional encoding. Then we will do the multi-head attention. If you look at the attention model, okay, we know that we have the Q. Okay, we have the Q, we have the K, and we have the V. So the process will be, after we got this embedding, so we will take a look on the query. What is the query? And then check the keys. The keys is any kind of value from the previous memory, and then we will do the multiplication. After we got the result, we can do the softmax, and then we will multiply this result with the values. So after this, we will get the relevant info, and this kind of value, it will be used for the decoder. So the mechanism that we learn, like the x, okay, this is the value from the embedding, we can multiply with the width of q. So the x can be multiplied with the width of k, and the x it can be multiplied with the width of v. So q is the query, q is the query, k is the key, and v is the value. In the overall, the current attention mechanism, it is based on this formula. So the softmax q multiplied by k transform divided by the square root of d. D is the number of the dimension multiplied by v. And after we got this value, we will embed into the decoder. So this is the decoder. Yeah, if we look at the very brief, okay, so this is the overview. If you have the input, J Swiss Etudiant, so it is maybe this is a France, and then we will put it into encoder. We have another encoder, we have another encoder, another encoder, another encoder, another encoder. So this is the encoder side that follows the architecture that we already looked at before. And after we have this encoder at the end, it will be split into several of the output. Okay, we can split into the decoder until we got the result. Then the output is I am a student. So the transformer, yeah, we use what we already looked at the previous architecture. This is just the overview how the mechanism works. So you can look at the encoder and the decoder. In every of the encoder, you need to have the attention and feed forward. For the decoder, it's also the same. You have the self attention, and then you have the encoder decoder attention, and then feed forward. Okay. Then if we have the word Alice is, okay, then we will get the embedding of Alice. We will get the embedding of is. For the query and key and values, so we have the Q1, K1, and V1. Okay. We have the Q2, we have K2 and V2, and we can have the WQ for the matrix of query. We can have the WK for the matrix of key, and we can have the WV for the matrix of value. And yeah, we just perform the multiplication. So like what we did before. So x multiplied by WQ, okay, x multiplied by WK, and then x multiplied by WP. Okay. So this is the mechanism. After we have x, so we will do the multiplication for every of W, WQ, WK, WV, and then we will get the final value or the result value for Q, K, and V. After we have this value, we will do again the multiplication and we will do the concatenation. We got one value, which is Z0. So we will perform several iterations. Okay. We got the W1, Q, W1, K, W1, V, and then we got the Q1, K1, V1, and then we got the Z1. And so on. After we do several kind of iteration, we will multiply with the WO, or this is the weight for the output. At the end, we will get the probabilities, or this is the output, the result, or it results the Z matrix. So this kind of things, yeah, is just a matrix multiplication. And every time you do this transformer architecture, you need to provide the weight, and the weight. After you know the X and after you know the weight, so the remaining will be only the multiplication. So in the transformer, actually, there are some variants. There are 5 kind of variants that I want to explain, but now there are more variants, but let's just focus on those 3. Okay. So the other kind of variants, yeah, it is just the additional, but we will take a look on those 5. What we already learned on the transformer is the scale dot product attention. So this is the most common attention, and the transformer, we look into the Q, we look into the K, and we look into the V. For every attention, we will use this softmax function of the Q, which is the query, and KT. So this is the K matrix, and then we want to transform. So do you know the matrix transform? If we have the matrix like this one, 1, 2, 3, 4, 5, 6. So what is the, if this one is A, what is the transform of this matrix? Then we will get the transformation is 1, 3, 5, and then 2, 4, 6. So this is the transformation of the matrix. We got a Q and we want to multiply with the K transform. After we do the multiplication, we will divide with the square root of dk. D is the dimension of the word or the sentence that we want to pay attention. And then after we got the softmax, we will multiply with 3. Okay. So this is the mechanism that we already looked at before. So the scale dot product attention is the basic attention for the transformer. Okay. And we can use the multi-head attention. Okay. So in the multi-head attention means we have several kind of attention. So the head I. So I means a number. It can be 1, it can be 2, it can be 3, it can be 4, and so on. If it is 1, then it means this is 1 attention. If it is 2, then it is 2 attention. If it is 3, then 3 attention. So every attention, we will do the attention mechanism. And after we do the attention mechanism, we will do the concat. Concat means we combine. We combine the head 1, head 2, head 3 until it's, after we do the concatenation, we will multiply with a weight in the output. So the idea is like this one. We have the V, K, and Q, and then we perform the linear function, and we do the scale dot product attention. Okay, we do the scale dot product attention. After we have this one, maybe H1, maybe this is H2, this is H3. Then we will do the concatenation. And after that, we have the linear function to get the multi-head attention. The total computational cost is similar to that of single head attention with full dimensionality. So with this mechanism, even though we have many heads, but the computational cost is still the same. with the scale.product only. Position-wise feed-forward neural network. If we are dealing with the position, it means we need to understand the index. Where is the position of the word? That's why we will apply the positional encoding. So we will take a look later, the positional encoding. The positional encoding means I would like to focus on some words in particular position. So some of the words in some position, they will have a higher value, but in the less important position, they will have a small value. That's why we will need to use the positional encoding. So at the end, if we do with the feed-forward networks, the FFN, we will use this function. We will check what is the maximum between 0 and xw1 plus b1. After we got those value, we will multiply with the w2 plus the b2. So w is the width. So the width at initial state, it is random, but we will learn what is the best width. And then b is bias. So the bias means the error or the distance between the real value and the width. This is the position-wise feed-forward neural network. So we can look into the other kind of transformer. We call it embedding and softmax. So in the embedding and softmax, for every of the embedding, for every weight, we will have another embedding weight. And then before the linear transformation, we will do the pre-softmax linear transformation. So for example, yeah, if you look at this one, after we have the linear, we have the softmax. So if you look at the, yeah, this one is the basic transformer. So some of the previous works, they do not perform the softmax, but we can also perform the embedding and the softmax to make the result at the end of the result, it will be representative for the probabilities. Okay, and positional encoding. In the positional encoding, it is one of the new works, especially when we have a long sentence. If the sentence are too long, so we need to focus on some of words. So we need to know where is the position. The reason that the positional encoding has been developed, it was about the RNN. No RNN to model the sequence position. So we do not care about the position. That's why some of the researchers, they propose the positional encoding. And for the positional encodings, there are two kind of positional encoding. First, they will learn the positional embedding. Learn the positional embedding means you will learn any position, and after you know this position, you will do the encoding. This position, you will do the encoding, you will do the encoding for this position, and you perform the mechanism like this one. However, there is another kind of works. They use the sinusoid. So the sinusoid means they will use this function PE. PE. PE is the positional encoding. And there are two functions. The first function is using the sinus. And the second function is using the cosinus. So if you look at this one, we have 2i, the position, comma 2i. And if the position is 2i plus 1, 2i plus 1. Actually, this is the position in the word. If it is, if I equals to 0, then 2 multiplied by r, it is 0. If I is 0, 2 multiplied by I plus 1, then it is 1. So we can say that if it is in the position 0, we will do with sinus. If it is in the position 1, then we will go with the cosinus. So every of the I, we will take a look later with the example. We will perform the positional encoding 1 and the positional encoding 0. Let's have a break. Okay, I will continue after the break.